So I hope you're all good during the midterm period. It's kind of like everybody tired, right? Because I can see some of you are busying in the library or at home. So usually the attendance during the midterm week is terrible. But I hope you pay attention because the midterm classes turn out to be more important than others because this is the foundation that be built for the rest of the semester. It's not difficult, but it's just conceptually more important. Doesn't affect too much about your grade, but it is important by itself in terms of understanding why everything makes sense here. So just let me quickly review what we have learned last time. It's not a lot slide, so we should be able to finish this whole set this week. It's not going to take a long time for this set of slides. The goal of this is to introduce you the terminology, why you do sample, and you understand what sampling is. And then that's what in terms of the idea, that's why you learn sampling distribution. You learn that it's turn out to be what you sample is not known in advance, right? So that's why random variable works. And that's why we need to study probability. Why study random variable, right? Because starting from the first chapter, we do the data, and since then we just suddenly we just, okay, we're not working more on data, right? And now we actually get back to data. So the idea is that because the thing you want to study is population, and you're unable to study every single one in the thing you are interested in. So that's why I focus on some subset of it, a selected group. And this group, if you want to make a statement based on what you observe to the general, much larger picture, you need it to be representative, right? Otherwise, the thing that you see from the sample, smaller part of the population, is not going to apply to the whole population, right? So the main thing is very important, the sampling process. And our class will enable to tell you how to do it properly, okay? And usually a given from somewhere, or if you go to business, you do A/B testing, then in that case, that would be fine, right? Suppose you know now we are doing the career fair in our CYT, right? And one needs to see the ground floor of the CYT there. Now we're doing TikTok, right? And TikTok is a monopoly, more or less, right? In terms of the short video. And for them, they can have population data, right? But even if the company have all the data, are they able to do analysis based on the wholesale data? Probably not. Because it's very costly to do things on the whole global thing, right? And also the problem of the intellectual property war or whatever you call the China-US conflict, right? In that case, the data is not, in theory, say, the Chinese engineer cannot access to the Chinese US data, and US data cannot access to the China data, right? So there's a geographical firewall that forbids you to do it. So you really can't say have a global data set, right? So in that case, you have to rely on some sample, right? So suppose you want to do some study, right? And you are the US advertiser, if you want to do something, right? Maybe you really can't access the China data, right? So you have to rely on, say, the Chinese outside China to guess what's going on in China, so on and so forth, right? So even if you have SL data, political reason or operational reason, you cannot really study everyone. So there is some issue there. Also, there is some privacy concern. So also security concern, right? I don't want to give a data to one guy who have all the information of the company. So there's a lot of reason why, even though you have all the information, you really don't want to do it, okay? So you have to rely on sample anyway. So same as in many studies in the census, right? Even the government, all the data, they don't allow you to access the data, okay? You only have the choice of random choosing some sample of it. So even the government don't allow its employee to have the full set of data. So you have to rely on sample anyway. So even if all the things. So I hope I convince you that there's no way you can have population. Only if you where scenario, but usually doesn't exist in our application in business or whatever, okay? So just some terminology, right? So you are going to draw a sample from population, and then we call the population. We have a distribution function, okay? Of course, that is something is not random, right? That is the relative frequency, right? Also, we also call distribution, but it's actually the relative frequency, right? How many people like this, right? If you look at, for example, look at income distribution, right? You have how much they make for each guy in the society, right? And you have the mean and variance. And do note that these are all data from chapter 1, topic 1, right? There's no uncertainty. Mean is just adding everyone up divided by n. Sigma is like you subtract everyone from the mean and square divided by n, okay? In this is the case, you take the n, not n minus 1, okay? Because you have the data for everyone. So that's why they got population mean and population variance. But as I just argue, you're never able to have everyone in your data that actually you can touch, okay? Regardless of their operational constraint, privacy constraint, technology constraint, you can only have subset, okay? And because you do the sample is not, you know in prior what you're going to get, usually random sample, okay? In that case, what you're meeting, what you're drawing is a random variable, okay? And if you do a random sample, you random draw things, your probability distribution or the probability mass function, right? You will follow the same F. Okay? So that's why with probability, right? We draw one guy there, right? Then it will be same as the relative frequency from the underlying data. So the F, the population and the random sample the same. Okay, same F. Okay, assuming that you draw in randomly. Okay, if you don't draw randomly, they are not the same, and that means that this F different from that F, right? Then that means that your sample doesn't carry a lot of information about them, right? If you do not have the same F, that doesn't look really right. If you just basically suppose look at income data, suppose you only are not able to have data on very rich people, right? Then F is just looking at the people who are not so rich, right? Then your F, your getting is not the F what you want, right? Suppose you only get the poor people. So then what you get is the population focus on the poor people, forget the rich, right? Or you only get the rich people, you don't get the poor people, right? Suppose, for example, you only able to talk to the woman, not the man, right? Then your only data is this man's data or woman's data. Okay? So that's an issue there. And usually a sample size n will use capital letter X1. Okay, that is I want to emphasize why you have capital letter. Capital letter in our case is a random variable. Okay? If a data, well, use a small letter. Okay? Capital letter is always in our case, it's a random variable. Small letter means some it fixed number constant. That's the way. Not my invention, is all the textbook you read. Okay? Usually I didn't invent notation. Okay? I just make the notation that in all the other textbook, okay, to follow it. Okay. So as I said, we look at simple random sample. We don't talk about how to do sampling. We just assume we have that. And do note that this is very simple, but it's very difficult to achieve. Okay. To achieve it, you need to learn how to do it in stat department. Okay? To do something simple, it's not that easy. Okay? And why? Because you have to make sure that everyone have equal access lab, right? It's very difficult. Imagine you want to talk to income, right? Are you able to go to senior houses to meet old people? Are you able to meet everyone in kindergarten? Probably not, right? Not everyone is going to be everyone, maybe somewhere one live in the mountain, deep inside somewhere in the forest. You can't talk to them, right? Or not easy to talk to them, right? And you have to each one equally likely to be selected, right? And if you do the phone call, then those who don't use the phone, you can't reach, right? Or use internet, those people who don't internet will not do it, right? Or you just call it at the daytime, people work in the night shift, we're not able to do it because they're sleeping. If you call it at night, people may sleep early, so you can't reach them. So there's a lot of difficulties to make sure it is all right, right? So that would be a lot of issues, right? So one of the easiest things you can imagine is, suppose in switch K, you have now school, right, with more female than male, right? And in that case, when you do the survey, if you're half male and half female, then you fail already, right? I mean, not necessarily fail, but it's not going to be representative at all too much, right? Because you think that men and women are very different. I mean, maybe, I don't know, but depends on what kind of question you're asking, right? If you ask, say, how likely you go to do shopping, how likely cosmetics, and how likely you want long hair, right? Then many questions, then female and male are very different, right? In that case, then you would have problems, right? So that, but how to adjust is way beyond our class, but assume we have a nice data, okay? And how to get it, as I said, go to further classes. And then just the terminology, what we said just now, if n x1 to xn is a simple random sample, then that means that they follow the same probability function, the big P or small f or big F, the same thing. Okay? That means that they have same mean, right? Same variance. Okay? And if they're dependent, means that they have zero covariance. Okay? So that later you will see is very important, right? That's why we learn independence. Okay? And that means that the same median, same mode, same IQR, same kurtosis, same skewness, everything the same. Okay? There's no correlation at all. Okay? And some of you will immediately jump if you do finance. That doesn't satisfy all the financial data. Yes. If the financial data, what you observe this moment is highly correlated with last moment. Right? You look at stock price goes up. Last minute, what expect? Next minute, is it more like go up than go down? Go up, right? That's what we call momentum, right? In finance, right? The price tend to be correlated, positively related. Right? So, right? Or put it this way. Now the weather is a sunshine. I hope. I don't know. Let me check. Sunshine here, right? What do you expect next minute? Sunshine, right? If last minute is rain, you go expect more like it rain, right? And this time series correlation is very important. I mean, in many daily observation, right? And we're not going to talk about those. If you really want to do it, it will be they'll study further. Okay. But you talk about weather today and tomorrow, probably is okay to put that, right? So if the time is different, is long enough, it's okay. Right? But if this is close like 1 minute before, 1 minute after, probably it's not. Minute today and tomorrow, probably it's okay to say, maybe they are okay to be. Right? And also look at you and your friends sit next to you, right? And probably you share some similar interests, right? You look maybe like each other, clothing, those wearing the same color, or you have the same hobby or whatever, right? Then that means that if I collect the same thing in this room, I talk to you, I select you and also select one next to you, then probably get correlated. Okay, so that has to be a little bit more careful. But that's beyond the scope of our class to talk about those. Okay? There's a lot of geographical correlation, time series correlation, temporal correlation. So you have to be very careful when you do things. Okay? But as I said, beyond the scope of class. Okay, but that will be very important because I didn't talk about the first class, but when I talk about master class, when I talk about statistics, the first class I talk about is garbage in, garbage out. Okay? So if the data is garbage, no matter how good thing you're doing, it'll be garbage. Okay. And also I talk about, in those classes, I talk about machine learning, a lot of advanced technique. Okay? And people ask, okay, why you have so much advanced technique? And I still talk about basic technique. The reason is because of, if your data is good, the basic thing is already done. If your thing is good, even calculate the mean, showing the difference to a bar chart, you're done. You don't have to do all latency regression, ANOVA. Basically, you don't need it. If data is nice, you don't need advanced technique. But data is not good enough, you need a nice technique. Right? So that's why you see the AI or large language model. Why you need that technique? Why in the old days we can't have a simple regression or simple mean and do? Because language is very complicated. The data is so complicated, you can't really use the traditional method. You have to use a complicated method to solve this problem because the data is so messy, right? If you learn the textual data, it's not 1, 2, 3, or 5, right? The text, the same word can mean different thing and depend on where they are, right? So it's a lot of complication in languages, right? So that's why large language model can have a very complicated regression. We talk about regression at the end of the semester, but the reason why you need complicated statistics because of real world or underlying is very complicated. You need a complicated model to do it. If your thing is very simple, very easy, then you're done. Right? Suppose you really want to have a nice data on how people want to spend on your product, right? You just you look at the data very cleanly, collect the people how much they want to spend. You have very clean data, then you're done. You don't really need a complicated model, right? If you have a nice thing, you're nice. Okay. So I hope you understand why here tell you how different way you can get the data, right? For example, the certified sampling. Okay. As I mentioned, there's a geographical correlation, right? And different area have different thing, right? So if you want to collect data from Hong Kong, right? Probably you want to divide the area into Hong Kong, Kowloon, and New Territories. The area in Hong Kong or different district, right? CHK or Sati, Hong Kong U, right? And each school, you want to collect number of samples that proportional to the student body size, right? You may collect more data from CHK, less from CTU or Linnan because they're smaller, so on and so forth, right? So these are the idea behind them, but I'm not going into details for that because I don't think anyone would be worried too much about at this moment. And again, we start last time. It's important because this meaning of this class, right? What's the name of our class? Anyone remembers the name of class? What's the title of this course? Right, the statistics, right? And then we never mentioned statistics until now. Look, here is it. What statistics? Okay, statistic is it's a function of sample. Okay, sample is what? Sample is a random variable from the population. Okay? And then a function. Function means what? You give me something, I give you something, right? It's a black box. You fit in something, it give out something. Okay, and what does it do? It's just like you have data. Okay, and data will generate some get from it random variable, right? And you output something, right? It's reduction dimension, right? The data is very complicated, right? You get something out, right? Remember what we call summary statistics, right? In the first class, right? Mean, median, mode is a kind of reduction technique, right? Mean, median, mode applied to population. Statistics is applying to the random variable. It's a lot of things that asking you the question about data. The data is very complicated, right? So these are all example is sample mean and sample variance. Okay. Do you know what? Okay, maybe example you see what definition is. Okay? So we have this again now, but now it's a sample mean, not the population mean. Right? It's adding all the data over n. Do note that this is very different from chapter 1. Topic 1 with a small letter. You check it back. Now a capital letter. Why? Because they are all random variable. Before you collect the data, these are random variable. Of course, when you collect data, they become number, right? That's fine. But this is formula apply is derived. Okay, it's a function, right? Because it's a random variable. So this is a function of random variable, function of the data, function of the sample, and it is before you collect it. Okay, it depends on what you collect, right? So who you meet, right? Who you talk to. So that's why it's a random variable. Okay, different from the past, right? The topic 1 is data is given to you, right? It's who added up together, right? Add up all the data. But remember, it's adding up all the random variable. Okay, F, the big X1, the big Xn are random variable. Okay, you don't know before you actually look at the data. Okay, so that means that everything has expectation, has a variance. Okay, has a big P and big F. Okay, as probability, you can say probability over this. Okay, sample mean, as we will say for the topic this class, sample mean is a random variable. You have a distribution. Okay, later we'll show you it's for the bell curve when n is large enough. Okay, but before we say it, this is the first part. Okay, sample mean is a random variable. Okay, depends on who you talk to. Okay, maybe an example would okay, Let me draw an example quickly to show you what it is, but I think it should be trivial, right? So suppose I have a population, right? And I missed out one, okay? And I have missed two here, okay? And I have an elderly number 3, right? Okay. And I have a baby number 4. Okay. So if I have missed out 1 and missed 2, the data would be 1.5, right? 1 and 2 average is 1.5. If I get senior 3 and missed out 1, the sample mean will be 2, right? If I got baby 4 and missed out 1, then the average will be 2.5, right? So it really depends on who you draw, right? And you don't know in advance what the sample mean because it depends on whether you got the baby, you got the senior, you got a boy, and you got a girl, right? So you don't really know which one you get to. It really depends on actually who you meet. You don't really know in advance, right? But that's life, right? You don't know tomorrow. Now the question would be, we will talk about this in order, okay? Hopefully we should be able to cover all of them. This is very important today. The sample mean is, we will tell you why we care about this, because this sample mean is the best way to estimate the mu population. Okay. What I mean by that is if I want to guess, suppose, how much people want to pay for your new product. Okay. And you look at the population of one study place, say the Hong Kong market. You want to calculate in Hong Kong, the overall, the whole market, how many people want to pay for it on average. That is a mu, right? Then, but how can you guess this number? Is to say talk to 1,000 people, for example, randomly, and you don't know what in advance to talk to, but this one, depend on who you talk to, 1,000 people, you can calculate sample mean. Okay. Of course, depend on what. But turn out that this sample mean is a good way to guess what happened in Hong Kong. Okay. Although it's a sample, as long as you collect the data in the right way, this will be the best thing you can guess going on. Okay. So the first thing, of course, you want to know what will be the mean, okay, and what will be the variance of that. Okay, that is easier to do. And probably you want to also do the big P, small f, or big F, whatever you like. Okay, and it turned out to be, it's very difficult to do it. It's very easy to get the mean and variance. That's not difficult. To get the P and the F is rather difficult. It really depends on what actually is whole Hong Kong people, how they distribute. Okay? But luckily, when you have big N, okay, it will be a bell curve. Okay, let me say this point is very important. Okay, I hope I stick this in your mind, because this is something you may think bell curve is natural, but isn't this way. Okay, the whole Hong Kong can be like this. Don't have to be bell curve, right? So this is the ordinal data, right? Can be something mu here, something sigma square, right? This is the data. Okay, and what can be shown, your sample mean means what? If you draw numbers here, maybe draw 3 or 4 of them and average out, right? And this shape can be anything, okay? If n is very small, suppose you're 3 or 4, can be something like this, can be anything, okay? Can be coming like this as also, that's fine. Don't have to be bell curve, okay? Okay, but at least one thing we know, I don't know the shape, at least I know that the average of this, which means the expected value of this guy, okay, turn out later you will show you, is still equal to mu. Okay, that means what? If I do many sample, okay, but remember I just do once. But hypothetically, I do many of these sample, and average of those sample mean is same as the mu. Okay. But remember, in the world, I just do once, okay? But imagine I do many of such sample, I will have recovered the mu. Let me repeat what I said. I have 7 million people in Hong Kong, okay? If I talk to 1,000 people, I'll get one sample mean. If I do another 1,000, I get another one. I get another 1,000, I get another one. I have, say, do this maybe 10,000 times, okay? 10,000 times, I have, each time I have one sample mean, right? Average of this sample mean will very close to this mu, okay? But do note that I only do once, okay? And I don't do 10,000 times, right? I do one. But at least it's comforting to know if I do many times, I get it. Okay, so that is the thing. Okay, on average, it means you do many times, you get the right solution. Okay. Okay. The second thing turned out to be, if you have random sample, what's the variance of this guy? Okay. Turn out to be variance of this guy, which we will prove later. This is equal to sigma square over n. Okay, we can prove it. Okay, n is the sample size you're doing. Okay, n sample size, sigma square over n is sigma square, but n depends on the sample size. Okay? If each time you do a large sample, okay, then the variation of sample mean. Let me say it again. You have 6 million people. 7 million people. Okay, you do 1,000. You talk to 1,000 people. You got one sample mean. Sample mean number 1. Now you do another 1,000. Sample mean number 2. You do 1,000. Sample mean number 3. And suppose you do 10,000, right? You have 10,000 sample means. Okay, each time is a 1,000 observation. 10,000 sample means you can calculate the variance, right? Among these 10,000 sample mean. And it's 10,000 mean, the variation is just sigma square over n, smaller than original. Okay, n is 1,000, right? Each time I do 1,000. Okay, so that means that actually you can see that's how I draw the variance shrink a little bit, not as fat as before. Okay, imagine n is infinity, n is very large. Basically, every time you get so many data, you don't have variation, so don't worry about that. Now, the way I said, we will talk about that. Don't worry, just PV. We will talk about all this now soon. But what's fun part is the following: if your n go to infinity, means very large. What happened? This guy, or n is very large, will be something like this, with a bell curve. Okay, and probably ask how big is this? Actually, when n is more than 200, you already a bell curve. Okay, and if larger, actually, I will actually not put it. Even 30 is okay. And it's 30 above, it will be a bell curve, very close to bell curve. And when you get to 200, it's actually so similar to bell curve. And later we argue that it's very close to. This is what we call, later you see what we call the central limit theorem. The sample mean will approach to the bell curve when n is big enough. And of course, when n is bigger and bigger and bigger, you shrink into a very single line. Okay, because the variance drop. Okay, so this is the main thing we want to cover today. Okay? So, and there's a one thing we call law of large number, which means that when n is big enough, the bell gets crashed to a single line. And later we'll talk about the t-distribution, which we hinted in the last class. We'll talk about that. Okay. And then we'll talk about special case. We call binary data. You say you ask yes, no question. And that is become a binomial. Okay, later you see, so very close to binomial. But don't worry, we are not. This is the goal already, so it's an ambitious goal, but we're not going to do it today, all of them, but just highlight what's going on. Okay, so slowly, one by one. So don't worry about that. We're not going to be rushing over that. Okay. First, as I said, okay, if you have the many sample mean, okay, and the expected value of sample mean is original population mean. So how to read that? Remember, X bar is the sample mean, right? It depends on what you draw. Remember, the question is Mr. 1 and Miss 2, right? Can be Mr. 1 and baby 4, right? So depend on who you draw. Okay, I'll give you an example soon, so don't worry again. And this, the average of them, get back same as me. Okay. So do not, this may be confusing because you will notice that expected X1 is also mu, right? Each observation actually has same before, right? So you can imagine that the average of them is also a mu, right? If you draw everyone a mu, so average of them is also mu. Okay? So that's the main idea. Later we argue that next week, this is called unbiasedness, which means that what I want to guess on average is right. Although I do once, but at least I have confidence if I'm able to repeat this many times in the future. If I repeat many enough, I recover the truth. Okay, but I only do once, don't worry. So I just do once, but at least in principle, I'm able to get it. So this is a very nice property and also very not somewhat demanding, but not too demanding. Okay, somewhat demanding. And this later you see the requirement. Explain why next week we'll talk why the variance n-1 rather than n. When you estimate the sample variance n-1, you get unbiased estimate. N is biased. So we'll talk about the next week. So don't worry too much about at this moment, but that's what unbiased means. And on average, you get what's supposed you get. Okay. But do note that you only do once, okay? You don't do once, you just do one sample. But this is saying that if you do many samples, average of all the results of those samples, okay, we'll get what we want. Okay? You get the actual thing, but remember, I just do once. But this at least expectation is right. Remember expectation, right? Because I do one sample mean, two sample mean, three sample mean, right? Okay, so I hope I convinced you this is the graph, right? The population potentially can m different sample, but I want again, I just do one, okay? But potentially can have m sample, and this sample will have is sample mean, okay? An average of those sample mean is mu, okay? But again, just do one sample, okay? You only get one of those because unless, but of course in science you would have lab number 1 do number 1, lab number 2, so on and so forth. Someone repeat what you're doing, okay? But you're not doing that, okay? So let me get into the example so that you know what's going on. Suppose I have 3 number 1 to 3, okay? Now, if this is the data in the population, that means that I have guy number 1, miss number 2, and elder number 3, right? So the average in this population, only 3 people will be just 2 because 1 person. And this is a number, not a random variable, right? This mu is a number, okay? Of course, in the real world, we don't yet know this mu, right? Because this is, if you know why we're doing statistics, right? The mu is something we want to guess, okay? And if I just do sample size of 1, right? It means that I only randomly pick up one guy. Then I may pick up the guy with 1/3. I pick up the lady with 1/3. I pick up the elderly. I pick also 1/3. Okay. The sample means just the guy you meet, right? Because you just do one sample. So Sample mean can be 1 with probably 1/3, 2 probably 1/3, 3 probably 1/3, right? So on average, you're right, because on average, you will get 1, 1/3 of 1, 1/3 of 2, 1/3 of 3. Of course, which one you get, you don't know in advance. But if you do many of those, you get 2, which recover the sigma. Sorry, recover the mu, right? You don't know mu, right? Just like there's a box there, you draw one guy, it's 1, okay? Sample mean is 1. Draw the guy, miss number 2, miss 2, they get 2. If you draw the elderly, you get 3. Okay? But you don't know what you get, right? 1/3 of the time you get 1, 1/3 of the time you get 2, 1/3 of the time 3. But you only do one time. Okay. Now getting more fun is not to just get one guy, you get 2 guy or 2%. Okay. And here, remember, the 2 sample you get is independent. So you can get guy number 1 again. You get number 1 the first round, you may get number 1 again. Okay. You get number 2, miss 2, you can meet miss 2 again. Okay. Because each draw is independent. Okay. So you have 3%. You may meet number one again. Okay. Number one in the table, average is 1. Okay. That is this number. Right? You meet number one. The average is 1. You meet number 1 is 2. The number is 1.5. Okay. You meet number 1 and elderly 3. The average is 2. Okay. And these are all possible nice cases, right? And this sample mean for each possible case. And because you draw even probability, so each outcome will come with 1 knife equally likely. Okay, the probability of each outcome arrive is 1 knife, right? Because there's 9 probability and each one is equally likely. And that means that you have 1 outcome of 9. That's why 1 is 1 knife. Why 1.5 is 2 9? Because you have 2 outcome out of 9. Why 3 over 9 for 2? Because you have this, this, and this. Same for the rest of 2. Okay. So once you have this, that means that if you do this sample size of 2, 1/9 of time you get 1, 1/2 of time you get 1.5, right? So on and so forth. Then the expectation will be 1/9 will get 1, 2/9 will get 1.5, 3/9 will get 2, 2/9 will get 2.5, and 1/9 time you get 3. So the average 2. You get back the mu. Okay. If you do 2 sample, if you do many times, okay, that is what you get. Okay. But do remind you that you only do 1, so you don't know which one, because you don't. If you know, you don't know the answer, right? But you may end up with some of them you don't know. Okay. So this is number 3. Okay. I'm not going over that because it's a black, you know. So I just leave here in case you have nothing to do within the break. You can check if I do anything wrong here. Okay. That should be right. Okay. But if you want to check your idea whether you get it wrong, you can check the calculation. Okay. So as usual, we have 15 minutes break. Please do you reply. I see you soon. So you can see everyone is very tired, but I think we are doing slowly. Hopefully, you okay? God bless your midterm fans. Yes, I hope you have a good midterm. But we don't have midterm, so I hope we spare some time from this class to the other one. Hopefully you would. But do remember that we also have a quiz, right, in our class. So this, when you have time, you should do it. As long as you do it, then you get the credit. So make sure that you don't leave fun on the table. Just do it. And also, it's a good time to test your knowledge. Yes, everyone knows we are here. Weather today is a little bit changing a little bit. So simple random sample, also expectation of sample mean. So I think one of the key point is sample mean is a statistics, which is also a random variable. And yeah, I think everyone also got the expectation of the sample mean equal to population mean. Yes. That means that if you do enough sample mean, on average, you get back what you want to get. Guess, literally guess. Yes, we're guessing. That's true. O4 is fine. Although I know you're tired, but the answer is still a little bit comforting. You're very tired. So you see this new question. So you can see this exponential up. No one say not very tired, but you're going to be 50% is strongly very tired. So I have say one technique would be useful is to do mindfulness meditation. Very useful. If you don't know what it is, just deep breath. Okay, count 1, 2, 3. Then it's very useful. Just to relax a little bit. It's very useful because I don't have enough sleep a lot of time, especially when you have kid and when the newborn first 3 months already, you always don't have enough sleep. Then you have to do meditation, and deep breath can really helpful. And again, I guess it's very good to come to my class and take a nap, right? Or if you really can't sleep, the good thing is listen to my record lecture, then easy get sleep. Usually that's how I do. If I don't have enough sleep, I just listen to some nonsense math class. That's how I get sleep. Go to MIT class, listen to some crazy math class, and you easily got to sleep because you want to concentrate, and you can't concentrate, it's easy to fall asleep. That's my thing. Same as some of you here, right? We're tired, right? But you still morally you want to attend this class, but probably don't understand what I'm saying, or I didn't explain very well. I'm sorry about that, but it's good. At least give you good sleep. So give you some reason why you're here, right? So although you don't want to come to this class, right? Or you don't find it very useful, but at least it's useful for you taking nap. Okay. So let's continue. I hope if you have time to go over that, it should be right, but it can be proved correctly, so it should be right. There's no problem. So on average, you get back what you want. And you can actually see from this, you draw it, the P function looks like more like a bell, right? It looks like this, right? 2 is here, 3 is here, 1 is here. It's more concentrated in the center. And actually, if you do more and more, you will see the bell curve appear. But I'm not going to show you, but actually it will be like this. Okay. Do remember, you can look at this. Initially, this is a uniform distribution, right? 1, 2, 3, or 3, 2, 1, right? So at the end, it becomes a bell curve, even it's starting from a uniform. Right? Because 1 appear once, 2 appear 1 times, and 3 appear 1 time, right? It's a uniform in the beginning, okay? So this is a proof why mean of the sample mean is population mean, right? Now, the second one is, as I said already, variance of sample mean, okay, is the population mean divided by sample size. Okay, how to get that? If n is 1, that is not surprising, right? You guys get one guy, right? the variance is just same as the population variance. It's just one guy, right? It's no different from the origin. And if n go to infinity, well, you get as many data as you want, then it must be equal to this sample mean. There's no variation, right? Imagine you get every sample as many as you want, right? Of course, you know what's going on there, right? Suppose you have 6 million people in Hong Kong, right? If you get 1 billion data, right? Basically, everyone will have a chance to have it several times, right? As many as you want, then you don't miss anyone. Anyone appear many times, average of those will be just 0, right? Because there's no difference. Actually, you get more larger than your population, right? So, and at the intermediate case, that will be over n, right? That means the larger the sample size, the sample mean will be less variation, right? Because you cover most of the data, right? Because you have a large chance to cover most of the data. And that means that this is the case. Of course, you can prove it, but we don't have the time to go for the math to prove it. I'll give an example to convince you that what I'm doing is correct. Okay, I'm not going to prove it, but I'll give an example why it's right. But the proof is in the slide, but I'm not going to go over that. Okay, but before we do it, we want to define a term that you often see in many texts, what it is, but usually you can't. Sometimes they don't define properly. So what we call the standard error is the standard deviation of statistics. Okay? Okay. Remember, the sample mean is a random variable. Okay. You have variance and standard deviation, and very often the standard deviation of the statistic is called sample error. Okay. I don't know why they call it, but it just creates trouble, right? Why don't they just call standard deviation of that? But anyway, they just don't bother. So they could, because standard error of the mean is standard deviation of sample mean. Okay, so it's just simply square root, right? Square root the numerator denominator. Okay, so it's sigma over root n. Okay, so let me not prove, but demonstrate why is the case. Okay, and so if you recall, you have num 1, 2, 3. The population mean is 2. Remember, this is not random. This is from data. And sigma is also not random because the data. Okay, you just simply add them divided by 3. It's 2/3. Okay, sigma and mu are deterministic, not a random thing. Okay, now below is a random. Okay, we've got a sample. If I have a sample of size 1, we know that 1/3 of time you get 1, 1/3 of time you get 2, 1/3 of time you get 3. Okay, and that means that the sample mean will have 1, probably 1/3, 2, probably 1/3, and 3, probably 1/3. Okay. And you take the sample mean minus the expectation. Expectation is 2, because this is this guy, right? We just learned mean of the sample mean or expectation sample mean is 2, right? So 1 minus 1 square, but 1 minus 2 square is 1. 2 minus 2 square is 0. 3 minus 2 square is 1. Okay. So the variance, remember, is this multiply this plus this multiply this and plus this, right? That's what he said, right? So that's what it. And turn out to be 2/3, same as what we said. Okay, that is sigma square over n is 1. So that's sigma square, right? So that's formula. This is to be equal to the sigma, right? This is the standard deviation. This is the variance of this random variable. Okay, and above there's no random variable. That's the variance. Okay. So now we see why we have a sample and population. They're different things. And now consider the case we have 2 sample size. Okay. So what do we get? So this, remember, we have 9 possible cases, right? If you still recall, 9 possible cases. We have 1 with 1/3, 3 with 1/3, right? 1.52 and 2.529, and 2 with 3.9. Actually, maybe 3.9 is better, right? Because that would be easier to see, right? 3.9. Okay. And it should be 1.9, sorry. It's a typo. Okay. The last one is 1.9. And you can calculate the variance again, right? So you just subtract each one from 2 and square. You get the second row over here, right? Everyone is -2, right? So this guy. Take the first row -2 and square, okay? And you just multiply each one, this 2 column, so this row, and add together, okay? And you will see, once you do it, it's 2/3 over 2. 2/3 is sigma square. This is n. N is 2. Okay. So that, I hope my confidence is right. Of course, I can prove it, but this is the case. And similarly, you can do the 3. Okay. You can do the same. As I said, I don't want to bother you with that. You can have fun with that when you have time. I don't think you have time because you're basically midterm anyway. So just believe me, okay? And believe your textbook. Okay. So this proof is here. And you see we use the idea of sum of the variance is variance sum to derive all this thing. Okay, but we're not going to do it. Okay. So we're going to talk about following is called law of large number, which essentially said when you have very large sample size, the sample mean is the population mean. Okay, let me repeat the statement. When we have super large sample, yeah, the sample mean will be exactly population mean. There's no variation. You can forget about probability. Everything you get is the truth. Okay, so if you have infinite time, right, you keep testing the same thing, you know what's going on. Okay? There's no uncertainty anymore. You know for sure what's going on. Okay? So that's how science works, right? If you know the Newton laws of motion, you learn all the physics law, you keep testing, you do every time you do, there's no violation, then you think everything actually we can discover truth, right? Because in long enough time, everything is time tested, that is approaching the right thing. Okay. So the idea is the sigma square over n, when n goes to infinity, right? N is large, this one goes to 0, right? Because this look like this, right? N, this is sigma square over n, right? And this drop like crazy, right? At the end it becomes 0, right? You plug this guy out, right? When n big and big, and this becomes 0 at the end, right? And do note that the mean is mu, right? So that's why you approach there, right? Before it's like very large variance, okay? And at the end it shrink, right? No matter how you shrink it, you will get to 0, it must be at the center. Right? So that's what I said at the beginning. Regardless of initially what the data is, okay? This is x, okay? And x bar, no matter what you do, no matter how you shrink, right? When you get the sample size smaller, then you will be larger, then you get closer and closer to, suppose this is the mu, right? You get closer to the center, okay? And doesn't really matter how you go to it, but at the end of the day, you get smaller and closer, more strength to the center, right? Because and the variance gets smaller and smaller. At the end, this thing collapses. There must be a single line. Everything, you discover the truth, right? So it gives you an infinite period of time, okay? Then you will be able to discover the truth at the end of the day, okay? So there's no way you can deviate from the truth. If you keep collecting data, keep calculating sample mean, right? So you will discover what they are. Okay. That is called law of large number, okay? When you say about law, right, you learn physics, right? Law is a very strong thing, right? Law is something like it will be true regardless of what. They turn out to be, why is this law? Because turn out to be, this is very robust, okay? Turn out to be, seems to be like, regardless of what kind of stuff you're doing, at the end, you have long enough history, large enough sample, this is what you get. Okay? This very robust result. Okay? And this is a proof, okay? And what we mean by law of large number means that this is, I think, why we have to do it because definition. So consider any number you want to say, where how small it is. You say this is a random sample, okay? It will be within epsilon distance, must be probably 1. Okay. So remember the mean, I don't know, okay, it goes in this way. Okay, going this way, right? So basically this is the mu, okay? And this is mu plus mu minus epsilon, and this is mu plus epsilon, okay? It's essentially said, I used blue color, right? Okay. This blue color thing, okay, will be very close to 1, okay? When n is getting bigger, it's closer and closer to 1. Of course, at the end, it's infinity, this is exactly 1, okay? That is the formal definition of law of large numbers, okay? This is a proof, I'm not going to do it. It involves some proof there, not complicated if you learn M1 or M2, but I'm not going to say anything about that. Okay. So the next thing is what the second law is very important. It's called central limit theorem. Okay. In this class, we tell you 2 most important things you can show off to your statistics friends. Why? Because if they have to learn this, they will take at least 2 semesters or 3 semesters to understand what's going on. You just take half a semester, you're done, right? But these 2 are the most important theorem in statistics: law of large number and central limit theorem. Law of large number, as I said, if the sample size gets larger and larger, the sample mean will be the population mean. Okay, then no will be exactly that. And central limit theorem said, okay, how it looks like, right? How the P looks like, right? Because when we talk about that, is the random variable of sample mean will be as close as the closer it, right? But how close to it? Okay, because we say, remember what we said is the probability get very close to 1, right? But not exactly 1, right? Only 1 when you go to infinity, right? But before 1 is not, before infinity is not 1, right? The question is how it approaches infinity. What the shape? Okay, it can be any shape, and central limit theorem tell us that it will be a bell shape. It will be bell shape approaching to a line. Okay, that is what central limit theorem said. Let me repeat. It's saying that the sample mean, when n is large enough, you look like a bell shape, and you will bell shape approaching become a line. Okay? I don't know at the beginning when n is small, but n is large, you will start to look at bell shape. Okay, and the bell shape will be, of course, they will collapse into a single line there. Okay, it will be something like this. I don't know when n is small, but that is what it said is it will be increasing, look like this guy. Okay, and when you increase sample size, it will be something like even thinner, right? And you get it thinner and 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 thinner, become collapse into a single line. Okay. Then it will become law of large number, right? And big enough, but that's a bell shape go into infinity. Okay. So actually, as example, we have seen when 1, 1, 1, you just draw 1, 1, 2, 3, you draw it's just a bell. When the first one uniform, you draw 1, it's still uniform. And once you go to the second one, it looks like already a triangle. And the third one already look more like a bell. And this one is even look like more bell. You can try more at your home, then you will see the bell eventually comes in. Okay, it will be a bell shape. And this is become very small, right? You get 1 is very unlikely, right? Because how you get 1, right? When 4, you will get 1. All time get 1, right? So you're 5 or 6 or 7, you get all the 1 is almost impossible. So all this thing will collapse down to 2. Okay, so that's the idea. Not going to argue with that, but this is exactly usually what do you mean by central limit theorem. Okay. When n get large, the sample mean will be a bell curve following mean mu and sigma squared. Okay, so that means that when n is large enough, you have this, right? The sample mean. I don't care initially what the shape looks like, the x, right? The f, right? But this will be a sigma square. The way like this. Okay, so this is, I don't care initially what it looks like. When n large enough, bell curve, the sample mean. Okay, so that's why we want to learn bell curve. Okay, because it should follow the bell. And if this follow the bell curve, that means that this follow standard bell. Is that clear? Okay. And probably you will ask, how big is the n there? And for daily application, more than 35, you can apply. And that means that it's very easy, right? I mean, when you have less than 35, in business, almost 0, right? In medical test, you may have less than 35 because how many people can do operation can be limited to, can be less than 30. Okay? In those cases, you would have some other method to do, but in our model, that should be fine. Okay. Okay. Because this is the case, then you can simplify to this z, right? 0, 1, right? 0, and 1, right? By taking this guy, right? Because this is standard. Take a square root, right? So that's divided by the standard error, right? This guy is called standard error, right? Now, is that okay? Now, once we have that, we can have some exercise. Okay. So suppose the population have mean 5, variance 64. Okay. I don't know whether bell or not bell. I don't know. Okay? It can be anything in the shape. Okay. Population because, but suppose you have 100 sample from that, okay? And what's probably the sample mean is no more than 4, right? How can you do that? Because when you have 100 sample, you can apply central limit theorem. Okay? Although I don't know what underlying is, but the sample mean will follow the bell. So that is very important, right? I don't know whether the Hong Kong people willing to pay for a new product, what to say this. But the sample mean will be a bell shape. Okay? When n is larger than 30 something. Okay? 35, I can apply central limit theorem to say the bell curve. So that's very powerful, right? Because I don't even worry about what does it look like, right? It can be any shape, can be uniform, can be anywhere weird shape, okay? I don't have any clue what is going on because no one knows what the shape is, right? Before you do it. Okay? You only collect data, right? But turn out to be, you don't need to know. And we know it's a bell curve. Okay. So when you know this, follow the bell curve, right? So we have the mean of 5. Do not have a little bit different here. It's sigma. This is sigma square, right? This is n, right? Have to be careful, this guy, right? Sigma square over n. All right, so that would be the main thing, okay? So you have this, you convert to z by minus the mean mu, right? Over sigma over root n, right? Okay. And once you do that, you can calculate this. If you forget how to do it, you look at the table or Excel function. What this Excel function is the norm, right? Dot s dot this negative 1.25 true. Let me do it exactly as here, right? Let me do it in the Excel. Since I want to make sure that you know what I'm saying. Okay. So why not? Standard, this, negative 1.25, true. Okay, so that's how you do it. Norm.s.this, that is a set table, right? You put a number because you're looking at the z is less than 1.25, right? So that's the case. Let me draw a picture again to make sure that you see what's going on there. What I'm arguing is here. Let me draw here, okay? Mu is 5, okay? I don't know what the population looks like. Can be anything, what you like. I don't know. It's something I have no idea. Okay? I just know the mean is 5. And the variance is 64, okay? Don't ask me how I get 64, okay? There's some way to guess it, but suppose I know it, okay? We will talk about how to guess this guy later, but suppose I know this guy, okay? And what we will know is, I don't know how X bar looks like when n is small, the sample size, but when sample size is as large as 100, okay, large enough, I can say I also have 5 here, and it's a bell curve, center at 5, and the variance will be sigma square over root n. Okay. So it's 64 over 100. Okay. And the question being asked is no more than 4, which means the following. I have 4 here. Asking this area. No more than 4. Okay, less than 4. So, or you can rewrite this into the z, right? And this is 1, so this 0. And this sigma will be 1, right? Because x, right? And this 4 is equal to what? Negative 1.25. Okay? So it's asking this area. Is that clear? Yes. Which one? Sorry. Oh, that's a standard deviation. The variance is 64 over 100. So how to get this one is 4 minus 5 over the square root of 64 over 100. So it's 8 over 10 is divided upon 8. So that's why 1 divided by 0.8 is 1.25, right? Is that okay? So that is there. Okay. Is that clear now? So that's how you get the number there. Yeah, very good to ask a question, because I don't know what we don't know, or I don't know whether I expressed this correctly. Right? It's very good you ask question. Thank you very much. Since we have a small class, so let's ask. Thank you very much. Because you asked me, then we slow down a little bit. We don't have to rush anyway. Remember, we are ahead our schedule, so don't worry too much about. Just keep asking when you have question. Thank you very much for asking. If there's no question, I go to the next slide. Is there any question? Any question further? Okay. So if you look at the MIT courseware, you can often see the teacher is talking to students. Students keep asking questions, but in Asian culture, probably even I encourage you to ask, no one actually asks. So that's why you reply, but seems to be okay so far for this material. Is not complicated. Okay, so that's the idea. Number 5. Next, we want to talk about something what we call binary data. Okay, a special case. You will see what we said apply to binary data as well. But the thing is, binary data allow us to do things better. Okay, then repeat again. Binary data is a special type of data. You have 0 or 1. Yes, no question. Okay, and what we have learned so far will also apply to yes, no question. But yes, no question is some feature that allow us to do calculation more effectively. Okay, that's why we study binary data. Let me repeat again, because it's very important. Otherwise, you would think, why we talk about binary data? Binary data apply because it's a special case what we study. Central limit theorem, everything will apply. Okay, but because binary data, you will see binomial distribution or binomial apply. So a lot of things can be easy to calculate. Okay, and that save our life. Okay, make our life easier. Okay, you will see. We'll talk immediately what it is. Okay. So binary data is again yes no question. Okay, instead of asking whether how much you like to pay for the product, you just ask whether you like the product or hate the product. Okay, simple. 0, 1. Okay? Just observation is either it's no longer, as I said, it's no longer Mr. 1, Miss 2, Miss 1, Mr. 1 is 1, Miss 2 is 2, senior 3 is 3, and then you also have a baby 4, right? Binary data is like the following. Binary data in our world is just only 2 things. Okay? You'll be Mr. 1, say yes. Okay. And Miss number 2 will say no. Okay. And then maybe another old man is no. Okay. Maybe a baby, maybe a reptile bee. I mean, so like take, right? Can be anything. 0, 1, 0, 1, right? Sorry for my drawing. Okay. I'm definitely know you draw better than I do, and my son and daughter draw better than I do, but anyway. Try to draw with your mouth so you see how well you're drawing. There's no pen in this room. I mean, I can only draw with the mouse. So bear with me, just only 0, 1. So this is 1, 0, 1, 0, right? A bunch of 1 or 0. Okay, so special case. So do know that everything applies, central limit apply, law of large number apply, no problem. Okay, but we can do better than that. You will see. Okay, but 0 or 1 means that everything is by binomial. Okay, because S1 is success or fail. Right? Because everyone you draw is a binomial. If you draw n of them, it's binomial. Okay, you will see the logic here. Hopefully, it takes a long time for me to understand what's the logic. Okay, the pi is population proportion, which is the mean. because you add up everyone divided by n is the proportion of people who like, right? Suppose you have 3, 1, 2, 0 out of 5 people, right? Then you have 60%. Yes, right? 3 out of 5. Okay. So that's why the sample mean in this binary case or population mean is called population proportion because we have 1 or 0. Okay. The mean is proportion. Okay. Because you have 1 or 0, right? Adding how many of them divided by n, right? Count over the is 1 or 0, right? If you have 1 is yes, right? No is 0. The count is just total number of them, right? The sum of them is just count. Over n is just proportion, right? That's mere proportion, right? And then now, if you remember, the variance of this is just this. If you draw 1, right? Because that is what we normally distribution, right? Pi times p times 1 minus p. Okay, this by Bunoni, right? Mean is p, variance p times 1 minus p, right? This is Bunoni, right? Because you draw just one guy. Now, consider if you draw 1, right? Bunoni with pi, so mu is pi, and sigma square is pi over minus pi. Okay. Do note that the different, although you may be not easy to see, these two are different. This two is different from this idea. Because this is data. There's nothing related to different with the distribution. Okay. But this is random variable. Okay. It's saying that if you draw one sample, the likely you get 1 is pi. Okay. Means that, of course, you just draw one sample, either it's yes or no, right? 1 or 0, right? But if you draw 10 times, okay, pi fraction of them is 1, pi fraction of them is 0. Okay? And same the variance, right? You calculate the variance of many times you draw. Okay. So you see a difference, right? This is a random outcome is a random variable description. That one's data. Okay. And you will see the convinced binary data is mean and variance are related. If I give you the mean, I know the variance. Okay, so that is much easier. Okay, later you will see binary data avoid the problem of variance, right? The standard case, the mean and variance are unrelated. Okay, but in this case, mean and variance are related. Okay, so that is a very clear convenience of this particular slide. Okay, later we see this why they're related. Okay, and of course, I can't prove why this is true. I'm not going to go to detail. And we will call the sample mean or of binary data or we call sample proportion. Okay. Give the name P. But do note that there's nothing from sample mean, right? Because it's just 0, 1, right? Everything, the data you get is either 0 or 1. Right? Average of that is sample proportion. It's in sample, how people will like it or not. Okay? But do remember that is a random variable. The sample proportion depends on what people you talk to in the data, right? It's not something that fixed, right? And you will follow, if you follow the central limit theorem, you will be a bell curve. If you follow loss of number, you say P will be mu, will be pi if n big enough, okay? The central limit theorem and loss number applies. So the first thing is, as we said, because it's a special case, right? The mu of P, right? This is average of P, right? It's equal to pi, so this is nothing new, right? Because it's a special case, right? And this is the key part why binary data helps. Okay? Because the variance with sigma square is not independent of the population mean, right? If population proportion is pi, the population variance is pi times 1 minus pi. Okay? That means that I can simplify. So the key here, just to remind you, when binary data, the sigma square is pi times minus pi. Okay. If you know in the population who say yes and no, you calculate the sample proportion, which is pi. You don't need to calculate the variance. Of course, you can do the calculation, but it must be pi times minus pi. That's the math result. Okay, you can prove it, but I don't bother. But just take it. Okay. So that means that the pi, the mean and the variance are related when you have binary data. Once you know mean, you know the variance. Okay. Remember this unrelated probability. I give you a bunch of 1 and 0. Okay. You calculate the pi. That is the sample mean. But that is the mean, right? Not sample. That's the mean, right? You calculate the average of this data set. Okay. You calculate variance in the data set. Okay. It must be equal to the sample mean times the minus sample mean. Okay. It must be the case. You can try. Okay. Take bunch of 1 and 0. Calculate the mean. Calculate the variance. Okay. It must be variance and the mean are the same. Related to 1 minus. Okay. So just to make sure you understand what I'm saying, consider the following. We have bunch 1, 1, 0, 0, 1, 1, 2. What's that? Not count to 1, right? And then you can calculate the mean, which is average. Okay. This one. Okay. Look at the variance again. Variance P. Okay. Variance P. Let me show the formula to you. Okay. Do this. Okay. And let's do the following. This guy times 1 minus this guy. P minus 1 minus pi minus pi. Same. So this is what I said, right? It must be the same. No matter you change this number. If you don't like this, change 0. Okay. You change 0. You change this to 0. Change to 1. You see these two numbers must be the same. No matter how you change it. Okay. The sample mean, well, I mean, not sample. The mean and the variance are related. You give me the mean, I know the variance. Of course, I give you variance, you know the mean as well, but you know it. Okay. This is only true for binary data. They are not separate. Okay. So you take a square root of that, you get this result. Okay. Time's up for me. Good luck for the midterm for other class. I see you on Thursday. Stay behind to answer any questions you may have, but good luck.